In this video, we're going to talk about normal proportions, also known as z-scores. What we're going to be doing with these z-scores is basically looking at a way to standardize values. So when we have data from different sets of data that maybe the range is different, or there's something about the two sets of data that is similar that we want to compare them, but they're different enough that we can't just compare those scores directly. We go through a process of standardizing them to be able to do the comparison. So whenever we're going to compare values from different data sets that are similar in the way that they are. For example, if we wanted to compare how strong a woman was to how strong a man was, you wouldn't compare it just by looking at how much weight they could lift, because a man anatomically is going to be generally able to lift more weight. So you would want to look at how much weight could the woman lift in comparison with all women, and how much could the man lift compared to all men, and compare those relative values. So we're going to standardize these values. You can only do this with data that is approximately normally distributed, which is very typical for a lot of measurements that we'll be dealing with. So we're going to standardize the values by evaluating how many standard deviations each observation lies away from the mean of its data set. So for example, how many standard deviations is the amount of weight the women lifted away from the mean weight that all women could lift, versus how many standard deviations away is the weight that the man lifted from the mean of the weight for men. So that's what we're going to do by kind of standardizing that. Then we can compare those two standardized values and assess which observation is more extreme. If the women can lift more weight relative to all women than the man can lift relative to all men, then we can use that comparison to say, relatively speaking, the woman is stronger. And we call this standardized value a z-score. So the way that we calculate this z-score is basically determining the proportional relationship. So z is going to equal that standardized score, and we're going to take the data value, the actual data value, minus the mean for that set of data's mean, and divide it by the standard deviation. So back to our example again, we would take the actual amount of weight that this one woman lifted, subtract from that the mean weight for all women lifters, and divide by the standard deviation of the set of all women lifters' weights. Now when we do this, we're going to find that we could have two possible signs on our standardized score. If the data value is above the mean, then the standard score is going to be positive. If the data value is below the mean, then our standardized score is going to be negative. So just from the sign on the standardized score, we'll be able to tell whether that person performs above or below the mean relative to their population. So again, the z-score is how many standard deviations away from the mean that person's score is. So that means if their score, or say the amount of weight that the person lifted, was exactly the same as the mean for their data set, their standardized score would be a 0. So again, the z-score is great for comparing two similar but not the same sets of data values. Another example may be women's shoe sizes to men's shoe sizes. It might be the length of time it takes somebody to do something who's 20 versus the amount of time that it takes somebody to do something that's 50. So, very similar types of things, but different in some way, different enough that we have to compare the two. As we talked about in class, another example would be SAT scores versus ACT scores. SAT scores are measured in the hundreds, ACT scores are very small numbers. So we need to standardize those two to be able to compare how they did relative to everyone else in their group of scores. So let's look at an example here. So again, for all of this to work, we need to be working with a data set that's normally distributed. So in any problem, that's something that you're going to need to make sure is true. If the data set is skewed, then we can't use mean and standard deviation, therefore we can't calculate a z-score. So in this example, the distribution of IQ scores for a group of middle school students has a mean of 100 and a standard deviation of 15. Assume that the distribution of IQ scores for college students is also approximately normally distributed and has a mean of 115 with a standard deviation of 18. A middle school student's IQ score is reported to be 134, while her brother, who's in college, has an IQ of 144. How do these scores compare? So to kind of summarize this and look at what the question is asking, we have information for college students, one particular college student, and also the mean and standard deviation for all college student IQ scores. And we have the same set of information for a middle school student, that one student's IQ score as well as the mean and standard deviation of all IQ scores for middle school students. So we're going to calculate the z-score for both, calculate the relative value, how many standard deviations away from the mean is the middle school student and the college student, and then compare those standardized scores. So since the data sets are different, we calculate the relative value by doing a z-score and comparing that directly. So the way that we're going to do this is by comparing how far away from the standard deviations from the mean they are. If one of the students is one standard deviation above and one is one standard deviation below the mean, obviously the person who's one standard deviation above has the higher relative score. That relative word is very important in the comparison here. They didn't have a higher score. Obviously, when we just look at these two scores, the college student has the higher score. It's the relative score relative to the rest of the people in their population that we're interested in looking at. So we pull out the important information. So for the middle school sister, mu is 100, sigma is 15. Her actual score, the data value, is 134. For the college brother, mu is 115, sigma is 18, and his score was 144. So now we're going to calculate the z-scores. So for the middle school sister, you take the data value minus the mean divided by the standard deviation, and that comes out to approximately 2.27. And for the college brother, same thing. Data value minus the mean divided by standard deviation comes out to 1.61. This is a very important formula that you're going to have to learn because you're going to be using it several times. So data value minus mean divided by the standard deviation. So now if we want to compare the two of them, obviously just by looking at them, the z-score for the middle school sister, 2.27, is higher than the z-score for the college brother, which is 1.61. So it's pretty obvious just looking at those two scores that relative to their peers, the middle school sister has a higher z-score. That's kind of the interpretive language that you would use here. Relative to their peers, the middle school sister's IQ score is higher than the college brother's score. Again, that relative word is very important. The college brother's actual score was higher, but the relative score was lower. So if we look at what that means graphically, if this is our normal distribution curve with 1, 2, and 3 standard deviations marked above, the middle school sister is scoring here with the green arrow, a little bit above 2 standard deviations, and the college brother is scoring below 2 standard deviations. So you can see that actually the middle school sister has the higher relative score of those two. So that's what we're going to be using z-scores for right now. Is, one of the important things we can do with that is use that as a way to compare data from two related but different sets, judged differently, units differently. Something is different about them, but they're related enough that we can do a comparison between the two. Z-scores and the calculation of those is also going to form the foundation for future statistical topics that we're going to study.